So I'd already covered these content. We will look at each of it one by one. So speaker verification, voice-based biometric system for identity verification. We have other methods such as fingerprint scanning, facial recognition, and speaker verification is non-intrusive in all these cases. It requires only microphone, whereas we need a scanner for fingerprint and camera for facial recognition. So similar to that, but this speaker capturing indicates that you just require a microphone placed anywhere. The speaker verification is a key subfield of speaker recognition. The text-independent speaker verification captures the data that allows speakers to have to represent their speaking ability using any phrases or sentences. Whereas in text-dependent speaker verification, they have to specify the specific term, word, or terminology along with the phrases or sentences for making a verification on the based on the accurate match. So determining if the speaker is who they claim to be is what the speaker verification job is all about. So here in the speaker verification, the biometric process, where the identity of a person has to be verified based on their voice, it compares an input voice against pre-stored voice samples to check for a match. So this is the job. So input is known speech, and it is a process using the feature extraction from these voice. The training phase is generating a model for this features. Once you have the prominent unknown, that is the verification of the speaker. So the same component, feature extraction and resemblance measurement based on the already trained model, and you try to create a evaluation wherein you may generate an accept or reject part. So here we try to utilize the depth first ResNet for speaker verification. It is used to improve the efficiency and accuracy of speaker verification by focusing on extracting detailed voice features while minimizing computational complexity. So here the transformation model. This module helps in adjusting the input voice signals to different formats or conditions. So it enhances against the noise and ensuring robust verification here. So going through the literature survey, most of the content have been taken from IEEE ACM transaction or audio, speech and language processing, or from IEEE signal processing letters. So in the first paper, self-supervised learning with cluster-aware DINO for high-performance robust speaker verification. This method utilizes a self-distillation cluster-aware training. So here the loss gate and the label correction are involved, wherein the merits have it has got high EER improvement. So what is EER? Equal error rate. So no label data required over here and comparable to fully supervised systems. And the demerits are lines on clustering quality for pseudo labels is there. In the second work, cosine scoring with uncertainty for neural speaker embedding. So here is a comparative measure that has been incorporated. It introduces uncertainty-aware cosine scoring to handle speaker embedding variability using uncertainty propagation from embedding to scoring backend. So this is quite crucial because we are need to maintain the speaker embedding and manage that with the scoring ability of the cosine format. So it achieves 8.5% and 9.8% EER and min discrete cosine format reduction. So computationally, it is efficient. The demerits captured here is complexity added by uncertainty propagation. So in both of these words, we have to combine the EER to be evaluation metric along with min DCF in our work as well. The other paper, robust speaker verification using deep weight space ensemble. So here the weight space ensemble of base and fine-tuned models are required. This has a significant performance improvements across various conditions as well. So the voice is now traced with the multiple models, and the ensembling of that using the weight space is giving a robust and improved model. But It requires multiple models, okay, since it is having non-sampling for optimal performance. In the fourth paper, you can see a lightweight CNN conformer model for automatic speaker verification. It combines lightweight CNN and conformer blocks to reduce model size while maintaining the performance. Here again, it achieves 60.6 parameter reduction and a very less EER, 0.61% only on Vox Collab data set, outperforming previous models. So it's a very high-end model, may face limitations in further reducing computational overhead here. So in the fifth paper, it orients toward a different model based in self-attentive speaker embeddings for text-independent speaker verification. So this is concentrating on the text-independent speaker verification, uses Bayesian self-attention for multi-head attention systems to avoid attention redundancy. Also, it improves EER by 26% on Vox Collab dataset and 9% on uh, another dataset, SITW, effectively reduces attention redundancy. The Bayesian inference adds computational complexity and requires specialized optimization techniques. In the last paper, the incorporating visual information in audio-based self-supervised speaker recognition, the iterative self-supervised learning and with clustering and audio-visual representation learning is performed. Here, the merits are it outperforms previous self-supervised methods. Robust pseudo-label generation is also performed here, and it can improve the clustering accuracy more here in this paper. So, moving on to the system design of our work. So having seen all these voice-based identification is required, the speaker verification here in our work involved the depth-first ResNet and the Gemini model for identity verification based on voice characteristics. So it utilizes these generalized data set, VCTK, CSTR corpus for speech data. The feature extraction extracts MEL spectrogram features from audio samples using pre-processing steps. So why this is required? Because the audio samples are not, as it is fed into the neural network, it has to undergo a request model, and this MEL spectrogram brings out the relevant features of the voice based sample sets in a ultimately better way with time and frequency domain given the core importance. So data set splitting here, we split it again with training and test set. The model training is basically using the DF Resnet of Gemini. Is trained using Angular prototypical laws to enhance speaker distinction. So this is where we fine tune the parameters for our building the model. So we bifurcated it into two parts, the enrollment phase, where initially the users or the voice-based system is being activated to hold the data. It generates speaker-specific embeddings for individual new users. Embeddings are generated using trained model and normalized and stored in the database. In the verification phase, wherein the daily commitment for identifying the user, the test speaker embeddings are generated using trained model again and is normalized as it is in the enrollment phase. But in the second part of the verification, it does compares the embeddings using cosine similarity, compares embeddings of the previous enrollment phase with the current verification phase. And finally, based on the similarity scores, the system verifies if the speaker matches any enrollment identity. So this is the diagram, the entire architecture system design for our work. So you can see the feature extraction model. So it uses the corpus of ECTK and CSRT corpus. So the raw audio files .wav format is loaded into our pre-processing, wherein the feature has to be converted and given as the MEL filter bank features extracted from the audio. So the process is frame blocking, that is its segments. Okay, so and then you have windowing, then Fourier transform applied to it, power spectrogram in order to convert it into MEL filter bank, that is apply MEL scales and logarithmic compressions, and finally the MEL spectrogram. Basically time frequency representation of the audio signal is now extracted. So this is now the data that is the corpus is being converted into this MFB format, and now we will split that across as train and verification or test set. And once you have that, you feed it to the enrollment phase. And so here in the enrollment phase, again, we need to do a process with the generating the model. And again, you have the verification phase where it compares the model with the verification. In the meantime, we have the development phase wherein we try to actually promote the working of the model using core loss control, and that is the angular prototypical loss, which is controlled over the given model. So in the enrollment phase, as you can see, the MFB features from the enroll set is given to the trained model, loaded from the data, and the speaker specific embedding generation is created. So once you have that, it is converted to the tensor level, and it is normalized. The scaling factor is applied as well, and it is applied with L2 normalization, scaled embeddings, and aggregate the features. So you have that as a part. The model actually is trained here. That is the development phase. The training and testing is done here. The hyperparameters are being projected for the DF Resnet model. It trains in a loop level. So it has this model instantiated loss function, and the optimizer is working on the hyperparameters to extract the more accuracy with the features. And finally, you have the validation loop wherein it tries to work with the 10 cross validation. So the validation data batches train model with angular prototypical loss, and it finally gives the ultimate accuracy for both the enrollment and verification. Here in the verification, given the newer or the instant voice signals, the features are extracted and similarly converted as in the case of enrollment. The L2 normalization is done over that, and speaker verification model is now compared with the given data from enrollment and the verifier model. It's compared with the cosine similarity, and the score data is given a threshold. It accepts and it rejects the user. So this is the entire stream of work that we had performed, and this is the transformation model, basically the DF, that is the depth first ResNet model. So here I've given the hyperparameters in the within the block. So it just gives a model of the entire ResNet. So MelSpec program is the input, and initially the convolution layer, then the transformation model with feature partition, and you have the feature fusioning also happening here. When we perform feature fusioning in normal levels, here we have done it using dynamically acclaimed feature fusioning based on the levels of the interactions of embeddings. So this is what is crucial in our work than the other works, wherein simply pooling or a meaning process will happen. Here it is not so. We either do a mean pooling, or we try to interact to have a one mean convolutions, and then we have this downsampling. That is the need of the ResNet, and then rest block, then downsampling again, then transformation model, the same transformation model, then rest block and downsampling and transformation, and finally we have this, which is now ended with the CNN and ReLU part. So here in the transformation model, you can see that each transformation is now the input feature F with the n dimensions and t frames. So this feature partitioning is divided into fi features. Okay, so some subsets with t frames and l dimensions per frame. So within the 1D convolution, it is now given out as QL, and the input channels are given out as L and Q output channels. So the feature partitioning block here, it splits the feature into fs as a given as a what do you say, uh, the values of the feature f is an element of r to the power n by t, so dimensions by frames. So each uh, ResNet block is now J subsets is now have handled with Fi, which is an element of R to the power L by T, along with the channel for frequency. So the feature fusion block captures correlational information between feature subsets using operations like 1D convolution, mean pooling, and interaction layers. So this again gives you the information about channel-wise feature refinement on the attention mechanisms. So the transformation model is now captured, and the next block that we can see is the attention mechanism for our work. So here in the attention mechanism, it enhances important channels and suppresses irrelevant ones to focus on key features. So we have the captures the channel frequency and time dimension in global context and local context. Global aware parameters is now provided in the convolution with batch normalization and ReLU, and the second layer of convolution model with batch normalization, and similarly it is combined again to give the global context and local context, but at each attention and capturing using the sigmoid level. So this is what we have created in the attention mechanism. So, given the intricate details about each of the modules, pre-processing adjusts raw audio amplitude to a uniform range purely to control volume, prepares the audio for subsequent transforms, MEL spectrogram transformation. It converts raw audio into time frequency representation, and here it transforms 1D audio into 2D, highlights perceptually the important components, and transform module. It performs multi-scale and multi-channeling process and learns robust features, not just simple transform, but deep adaptive representation. And the L2 normalization is basically to normalize the embedding to unit length, to allow comparisons based on direction, ignoring magnitude, different from raw audio normalization. The training loop in our system design, it's a forward plus back propagate to minimize the loss, and to learn basically to learn network weights, adjust the network itself. So validation loop is forward pass without back propagation to evaluate the network's performance on unseen data, guides the hyperparameter tuning on its own. So the enrollment module stores finalized normalist embedding and to create a reference vector against which the future samples will be compared. Here in the verification model, it computes similarity against stored embeddings. So this is where the final identity is being matched, is to either reject or accept the trained model. So the decision model apply a cutoff to the similarity score and does a job on the match fixation. So the novelty introduced in our work, depth first design prioritizes deeper networks over wider ones, which has shown to be more effective in speaker verification tasks by improving performance without significantly increasing complexity. And using multi-scale attention feature fusion, AFF schemes dynamically fuses features. Okay, so here this approach is superior to fixed weight fusion methods like element-wise addition or concatenation commonly used in traditional lightweight models. Most of all, the model is built combining angular prototypical loss for enhanced verification. So this loss aids in optimizing speaker verification by enhancing the distance between the speaker embeddings. The different speaker embeddings is now captured at this point. This loss function can improve the discriminative ability of the embedding generated by the model on its own. So just browsing through the detailed models. So the key components, the audio is required to be converted to MEL filter. Okay, so MEL spectrogram. So here you apply the short time Fourier transform, then apply the MEL filter banks and convert power spectrogram to decibels. So here is the um, and here is the short description of our pseudocode work. So there's an intermediate output with 2D array representing the long scale MEL spectrogram dimensions corresponding to the number of MEL frequency bins and the number of time frames. So the continuation of the same code. And finally, processing it, the intermediate output is 3D tensor. We captured actually the 4D tensor here, converted feature as PyTorch tensor. Then this needs to be fed into our deep learning model. In module 2, the development module, the learning speaker independent parameters needed for capturing the specific speech characteristics during development. The universal background model of Gemini DF Resnet training happens here, where the learning of speaker independent parameters takes place through the large sample of speakers. So here we have the input as MEL spectrogram. So the key components is reshaping the MEL spectrogram with this N by M, where N is the number of speakers and M is the number of utterances per speaker. So each speaker has got utterances to around 160 level. So MEL spectrogram dimension is 80 and the frames in dimension is 160. So embedding generation reshaped spectrogram model is passed through this Gemini DF Resnet 34 level based speech embed model. It does 512 dimensional embedding for each utterances. So reshaping for loss calculation, we have the CNM, wherein each speaker with M utterances, each represented by 512 dimensional vector. So this is model 2, where the development phase happens. Reshaping for loss calculation block is the core importance based on the embedding generation block. And then it undergoes the training block and validation block. So model 2 pseudocode is given as such. You can see the intermediate output is that the training data set that has MEL spectrogram features or MEL filter banks, MFB, used for training the model. Validation data set with MEL spectrogram features that is used for validating the model after each epoch and schedule the learning rate accordingly. So model initialization for training and capturing the loss function, and the gradients in capturing the loss. So this output provides feedback on how well the model is training by showing loss and accuracy for both the training and validation sets at regular intervals. And then moving on to the enrollment module, the process of learning the distinct characteristics of a speaker's voice, which is noted, and it is held as an embedded format in the data. So using this only, we can compare with the verification phase. So the distinct characteristics of the speaker's voice are used to create a speaker-specific model, and the data set is split again into enroll and test set. Instead, we can call it as train and test again. It gets the embeddings of MEL filter network features are taken, and ResNet model is used to generate the embeddings. So here the embeddings, and over and above the L2 normalization is imparted over it to input to the tensor mode. So this is the flow: split data set, generate embeddings, apply normalization on the embeddings, and average embeddings for each speaker. So the loading, train and test, and embedding generation pseudocode is given as such. And after splitting, you have the enrolled database and the test database with the normalized filter. So the module 4 is the verification module. It is similar to the previous one. The distinct characteristics of the claimant voice compared with the previously enrolled claimed speaker model is to determine if the claimed identity is the correct one. So load the enrolled embeddings, get embeddings, generates the embeddings for test utterance by splitting it into smaller segments. An L2 norm is applied over it, and you need to perform the verification using the speaker's embeddings, and cosine similarity is applied to it to extract the similarity. So you have the test utterance generation block after the load enrolled embeddings, applying L2 normalization over it and capturing the similarity using cosine, and reject or accept the verifier. So the loading model and embeddings generation and normalization, and performing verification. So intermediate output after splitting two data frames, you have this, and we capture the error here as equal error rate based on cosine similarity matrix between the test and enrolled speaker summary. So next, moving on with the captured results. So basically, we work with the dataset CSTR corpus. So this is a multi-speaker corpus. There are 109 native speakers, and with 400 sentences by each of the speaker. So we have content from TISB and TADB, so including newspaper text, the rainbow passage, and an accent elicitation paragraph. That is text independent and text dependent are the two variants we have. So text dependent are the rainbow passage and elicitation paragraph, whereas text independent are several newspaper articles given to each individual of the 109 speakers and capturing around 400 sentences from each of them. So we have, these are the sources, and the recording setup is in University of Edinburgh, and this is the dataset which is open source. So the applied performance metrics is equal error rate. That is the most important one. It depends on false rejection rate as well as false acceptance rate. Now, what is this false rejection rate? The percentage of genuine speakers incorrectly rejected as imposters. So it measures the inconvenience faced by the legitimate users. A lower FRR indicates the system is more user friendly. And false acceptance rate, the percentage of imposters incorrectly accepted as genuine speakers. So it evaluates the security of the system against unauthorized access. So the lower the FAR indicates the system is robust against spoofing or impersonation attacks. And here, combining finally the equal error rate, it measures the point at which the false acceptance and false rejection rates are equal. So it is a key metric for evaluating speaker verification models. So if it is having a low value, it is a better model. So min DCF, the evaluates the cost of making detection errors in speaker verification. The golden Gemini approach significantly reduces the min DCF across various test sets. So the detection cost function is basically dependent on cost associated with the false reject, cost associated with false accept, and the probability of false reject and the probability of false accept. So using this, we capture the min detection cost function. And these are some of the implementation output for .wave to MELSPEC program. The train and test folders and the utterances of each of the speakers with several files in the data corpus. And conversion to MEL spectrogram, the MEL filter bank. So the frequency time domain of the each individual wave file is now captured, and we have the gaps here. That is the audio signal is not that's a uh, no signal from the voice. So these are the some of the highlighted outcome that we can have. This is given fed in for capturing the model generation, and the important features from that is now easily captured by our DF. So here you can see the accuracy versus loss over several epochs of a run on the model. So accuracy basically tries to improve, and the loss is also decreasing on the higher epochs that we have executed for the model. And this is one interesting table wherein four speakers are taken with six utterances across 160 frames and 40 classification. So we can see that it closer to one is the where we identify the test speaker. So this is what we try to understand, that the heat map of the same is gives you that only a limited fields of test speakers will match to the enrolled speaker. And EER is quite high though, and we want it to be more lesser. But looking at the model generation, we find that the model across the confusion matrix, you can see that the axis gives us higher value. That is, the color domain also tells you that the other parts are the speakers, the true speakers with the classification given out by the model. The true speakers are given in the row wise, and the classification are given in the column wise. And across the diagonal, you can see that it gives a better accuracy, and there is a slight deviation in the classifier, but that is quite minimal comparatively. And we also applied the explainable model to the results, and saw which features or which part of the speaker tone is being captured. And for that, we applied the GradCam algorithm. And here we can see in the heat map that that is, the forward is the activation and the reverse is the specific gradient generation through the back propagation, which captures the intricate details of the features, which is going to be ultimately used up by the model in bringing out the accuracy. And these enable us to notify for each speaker. It turns out that it builds up in a different toning level. For speaker 234, you can find that the highest heat map of 0.08, which gives certain details on features with pitch and amplitude, all these being captured. For certain users such as P330, you can see that most of the component has been utilized by uh, on the middle level 0.04 to 0.06. So this is the kind of um, feature extraction being utilized for uh, capturing the ability of feature. So test cases and performance measure, the single speaker and multiple utterances have been done. So test if multiple utterances from the same speaker map to the correct centroid with high similarity. So it is done by calculating the cosine similarity for each embedding with centroids and verifies if the true speaker matches the predicted speaker. And multiple speakers and distinct utterances, so ensures that distinct speakers are not confused with one another. So we have the utterances represent each speaker, and similarity scores are computed for every utterance. So the predicted label is checked against the true one. The genuine versus imposter pairs are now given out, and the validation differentiate between the genuine and imposter pairs. Here is again the similarity matrix directly checks imposter cases when scores of for non-matching speakers. So performance measures, basically the accuracy and cosine similarity scores are applied. So these are some of the model built, and some errors from our model in speaker is not authenticated, the similarity score is not within. So there is a fault in learning because the speaker 333 has got different voice modulation when he entered in the development phase, that is the enrollment phase, and in the verification there is a different tone for him, so it didn't accept it. So whereas all the others, you can see that not authenticated has been given out properly. And so some of the okay, so the conclusion is the novel speaker verification technique has been generated, and the method or the model applied is depth first ResNet based on the Gemini model, and comprehensive evaluation showing high accuracy has been ruled find out here. And the future work is by applying multi-model, not just voice but also thermal imaging, then fingerprinting, then face, everything together, put together, we can just generate a biometric representation for security enablement. Domain adaptation has to be taken care, and lightweight model optimization is required as well. So I thank you all. So these are my references. Do you have any questions?